Okay, hello everybody. So we're now entering our last YouTube lecture and last section, 7.2. It's all going to be about continuous fermentation. So what we have here is not just like in 7.1 adding stuff to the fermenter, but continuously removing stuff from the fermenter. Remember, the fermenter is a well-mixed system, so whatever you remove will have the same composition of what is in the fermenter. And this is our last section of CBI. So when we look at the mole balance, we see this is the generic form of the C mole balance. First thing we note in this system of ours is that the flow rate in is exactly the same as the flow rate out. So effectively we just have one flow rate in and out that will be called Q. Once we have that, we know that the volume will remain constant because the density remains constant. And because we have a constant volume, we can now take volume out of the differential term. And really, it simplifies things because like before, we just have a concentration differential. And we can now divide by the volume. If we divide by the volume, we end up with the following equation. So this is what we end up with. It looks pretty similar to what we had before. This is what we had before. And now we have this addition term of inlet and outlet flow rates. We can now just have a look at what the three separate equations will look like. So I'm just going to bring them up. So there you have it. You have one for substrate. You have one for cells and product. So quick notes here. You will see that the substrate equation has two separate terms because now here we are feeding, and let's write it down, we are feeding substrate, and it's the only component that we feed. Therefore, you will have this component feeding to this term. So only substrate being fed. And then in terms of removing material from the reactor, you'll be removing not just substrate, but also cells and product. So these three terms you have down here, they will just be the outflow of the substrate, product and cells. Very important to understand that cells, actually you don't feed any cells, you make cells in the fermenter and then you lose cells through the outlet of the fermenter. Taking this equation that we just have and integrating it will give us something that will give us profiles. So depending on your starting condition, the profiles might look different, but you will typically end up with something that looks like this. Okay, so I'm just going to redraw this one. Okay, so what you will see is that towards the end of your fermentation, you've got to play around with fermentation times. You will find that if you have a look, and I'm just going to have a look in this yellow window, that you clearly see that the concentration change of all the components will be equal to 0. Okay, so what we reach after some time is what we refer to as steady state. There's no more change, and there's no more change in the differential. So that's when the continuous fermenter reaches steady state. And what we'll be showing here is, if we have a look at steady state here, we don't have to perform a full integration to be able to solve for steady state. We can solve for steady state algebraically. And this is kind of one of the things I wanted to show in this example. So let's just have a look at the equations again. When we go with the integration route of solving the equations, we basically say take the three equations and use the fermentation equation to solve for the differential equations. Okay, but what we're now saying is that the differential terms become equal to 0. So if the differential terms become equal to 0 at steady state, effectively we will have the differential parts of the equations falling away. And now we have a slightly different equation to what we have before, and this is an algebraic equation that doesn't contain any differential terms. So we'll slightly modify the fermentation equation so that we have an equation that looks like this that can be now solved with the function fsolve. Fsolve is an algebraic is a solver of nonlinear algebraic equations. So previously we used ODE int to solve for the differential equations, but if we get rid of the differential equations where the slopes become zero, we now have a solver of algebraic equations. Just to rewrite those equations out, please note they might look like three simple equations, but if we have a look at RS and RX and RP over here, please remember they get returned from the response function, and they are really very nonlinear functions of CS, CX, and CP. So all three these rates that gets returned from the response function are nonlinear because of the way mu and theta is described. So what the fsolve function will do, and this is very important because you'll just be running it, fsolve will really have a fancy search procedure that guesses a CS, a CX, and a CP value, and basically try and find the combination of three guesses that will satisfy all three equations. Every time it makes a guess, it will generate the three equations. It will call upon response function to get the corresponding rate values at those guesses of CS, CX, and CP. And then you will find a possible route. In the example I've given you, there is a route where you find a realistic value of CX, CX, and CP. Please remember, if I talk about realistic, we only have positive values of concentration, so CS, CP, and CX should all be bigger than 0. And please note that CS cannot be bigger than the initial concentration or the feed concentration that you feed in that inlet stream. So you have kind of a window of possible concentration values that you can solve for. Whenever you have solved with fsolve, make sure that the values are realistic. So lastly, and this is just a short lecture before you start doing the TUT. If we have a look at the four equations, it is kind of interesting to have a look at the C-mole balance on biomass. I'm just gonna take that one equation out. That will be the C-mole balance on biomass, and just slightly rewrite it. So you'll remember that Rx is really the same as mu. So what we have here is that Rx-Cx is equal to Q over V times Cx. So now you can see the Cx can cancel out, and what you end up is that mu is equal to Q over V. Okay, and Q over V, that's just, that's kind of important that you understand that Q is something, it's a volumetric flow rate that you set. Okay, so it's something that you decide beforehand, and the volume of fermenter is also something that you decide beforehand. So here we have two control variables that you can set. So what we see here is in this continuous reactor, and we refer to this continuous reactor as the chemostat, you have a mechanism to control the growth rate. So you are basically, when you're planning how you run your fermenter, determining what the growth rate, and remember at steady state there will just be one growth rate and one set of concentrations that leave the fermenter. So the interesting thing about a chemostat or a suspended cell continuous fermenter is that you can control the growth rate. Okay, and then just lastly, Q over V in fermentation literature is typically referred to as the dilution rate. It's just the definition of throughput as fermentation engineers and scientists uses it commonly. So it's referred to as dilution rate, and it has units similar to mu, which will be 1 over hour. So I think you're ready. You can now do 7.2 and learn your last bit of fermentation. Okay guys, so this is basically it. We have been fermenting for a few months now, okay, and I hope that something in your brain has fermented a bit, so that as you go into the exam, so let's just complete this picture. So a few months ago you came into the system, and a few months ago you came into the system, and we try and teach you something about fermentation. Now, like the chemostat or continuous fermenter, you are going out of the system. Okay, life's about moving on. So similar to the microbes, you'll be trying to get out of this fermenter. We have in this fermenter scheme of CBI, we have a special little separator that evaluates outgoing cells. We call this little separator the exam. So what this separator does is that it takes some cells, and you actually get this in fermentation a lot, cell separation. You take some of the cells out and you recycle them back to the fermenter. But that's only a small fraction of the cells. Most of the cells will be going out of the fermenter permanently. Okay, so you guys are still fermenting, still doing your last touch. Soon you'll be flowing out of this continuous fermenter and you'll be going into the little separator. My wish for you is that you have fermented enough so that you end up in this little stream. Okay, so guys, good luck. I hope you can do some pushing in the exam and do your tuts. Try and really understand. Hopefully exam will be doable. Goodbye.